So the last thing I want to talk about this classroom, goes very fast, is to talk about our student notes. So I posted these student notes on the website. There are 4 types of FIR filters. They can either be symmetric around the order n over 2, or they can be anti-symmetric, odd around n over 2. And the order themselves can be even or odd. And you might think, why the heck are we making such a big deal about this? These are just more ridiculous conventions. It's even worse than that. We actually call these things different types. Type 1, type 2, type 3, type 4. If our n is even, we'll have the length of h of n is always 1 plus the order, so it'll be odd. So the length of h of n's oddness or evenness is the opposite of the n. And we give each of these a different name of the filter. And why we do this, why we care about this, will be much clearer. Will be clear next lesson, not this. But just for now, realize 4 types of FIR filters. This is the way they're defined. Very quickly, I'll just go through the definition for type 1. This is our n, which is even. And for n, which is even, for example, 4, we have a odd length, h of n. That means it's always going to be symmetric, or h of n, around some point. It's going to be symmetric around n over 2. And I'd like you to take a look at how this derivation works. You can see that the coefficients for h of 0 are going to be symmetric around this n over 2 point. And that means that it's h of z's, we can kind of group here. We can say it's h of 0, but since that's the same as h of 4, we can group h of 0 times these two things when we find it's h of z. And because we can group them like this, when eventually we find it's DTFT, these groups here all form by Euler's identities perfect cosines. And because they're perfect cosines, it means its DTFT is going to be a real number. And that means that its phase is 0. And I calculate what the phase is. It's the same thing as I calculated earlier, minus the delay. And then the group delay is the derivative of this, which is just a constant 2-sample delay everywhere. 30 seconds left. So for any n, type 1, it's the DTFT is equal to a delay times a bunch of cosines plus this one center value. So here's its impulse response, here's its phase response, and its group delay is going to be n over 2, not a function of omega. And although I won't go over the derivation, there's a similar derivation for type 2, type 3, type 4. The only thing is that for some of them, the delay is actually not an integer. So you can have a non-integer delay of these things, which is kind of neat in a discrete time system. But the phase is always equal to minus n over 2, no matter what system it is. The group delay is always equal to minus n over 2. And the only difference is that sometimes your h of n will be symmetric around n over 2, and sometimes it will be periodic anti-symmetric around n over 2. And that's all I have for you.